Let me introduce you a study and approach to evaluate the classification method to predict the construction object state. After by Tatiana Goncharenko, Olga Solovey, and Bogdan Solov. One of the goals of a construction 4.0 concept for building industry is to use a digital solution for automation and robotization of all construction processes. So ability to remotely assess the condition is of a building condition is part of a construction industry transformation according to construction 4.0 concept. Machine learning methods, specifically classification algorithm, are used to automate the process of the construction object technical inspection. Multiple classification models are built to put the object depending on its technical condition in one of the categories: normal, satisfactory, unfit for normal operation, and emergency. The process to implement a supervised machine learning model for construction object technical inspection consists of steps. Collect the construction object data, clean up data and perform feature engineering, divide the data into training set, build the model based on the train subset, evaluate model based on the test subset, and finally deploy the model. The model deployment for the end user is possible only when model evaluation score indicates that model has good quality. So the method which are used to evaluate a model must produce the trustful result. The method which are commonly accepted, the method to evaluate the classification model which are commonly accepted among the scientists are based on the cell values of confusion matrix in case of binary classification. And those four metrics are sensitivity and specificity. The metrics will set the model's ability to correctly identify positive and negative classes correspondingly, and positive predicted value and negative predicted value. The metrics assess the model's error for positive and negative classes respectively. The values of other methods which are used today basically are the function from those mentioned four metrics. For example, F measure, the metric considers the model quality to correctly identify positive cases and the model's error for positive cases. Its formula is a harmonic mean of sensitivity and positive predictability. Metric correlation coefficient, the metric considers the model ability to correctly identify positive cases and model errors both for positive and negative cases. Its formula considers all four parameters: sensitivity, specificity, positive and negative predicted values. Recently, been submitted the studies which show that F measure may not accurately reflect the model's true ability to classify objects, and it is recommended to use the Matthew method instead. The problem has been illustrated with a couple of use cases. Three use cases are currently on my slide. So for a given confusion matrix of binary classification model in table 2 that needs to be read as true positive, the number of fit objects which correctly predicted by the model, true negative, the number of unfit objects which are correctly predicted as negative, as unfitted by the model, then false positive. This is the number of unfit objects which are incorrectly considered by model as fit objects, and false negative, the number of fit objects which are incorrectly identified by the model as unfit. In row number 1 of table 2, it seems that model made mistakes only in one object. So in number 3, line 1, we can see that both metrics produces the high score which is expected. In line number 2 of table 2, we see that the model had a lot of mistakes while predicting a positive instances. So basically 10,000 unfitted objects were treated as fit, and we see that PPV has value almost 0. However, the model still has a good prediction for the negative instances, so NPV almost 1. As a result, we can see that normal Matthew coefficient has value 0.6, which indicates that model has a weak ability to predict the instances, but F measure indicates that model has no ability at all to predict the instances. In line number 3 of table 2, the model incorrectly classified 10,000 fit object as unfit, which means that the model has the low ability to predict negative classes. As a result, NPV almost 0. Our model has a high positive predicted value. As a result, F measure score is high, which is not expected because the general model ability is weak, and Matthew coefficient indicates this correct. So, having a look at those 3 examples, we can see that both metrics could produce the similar results or be in agreement. At the same time, their values can be different. Since an effective binary classification model to predict a construction object technical condition may make a mistake when fit object is considered as unfit, as it was in line number 3, but must not consider unfit as fit, as in line number 2, it is important to not neglect F measure metric completely, but recommend the approach when it can be. The goal of our study is to propose an approach how to select the metric to assess a binary classification model for predicting the technical condition of the construction object. To meet the goal in the research, metric correlation coefficient formula and F measure formula will describe using maximized Jordan index, which value is possible to obtain when model does make mistake when predicting negative instances. The result of this work will provide the scientists the decision support method on how to select the method to evaluate. This slide includes the ROC curve of 4 commonly used algorithm to resolve classification task. It is Gaussian naive, it's random forest classifier, logistic regression, and support vector classifier. On those pictures, we can see that the difference between Matthew correlation coefficient and F measure, that is populated on y-axis, is different depending on a ROC curve threshold, where threshold value is a probability which is used by a model to decide that instance belongs to a positive class. Depending on the chosen threshold, the score difference between 2 metrics may be very close or may have maximum pair difference. Our approach proposed to use the optimal threshold on a ROC curve to calculate the difference between metrics. And this optimal threshold on the ROC curves, we are going to calculate using Jordan index. When both sensitivity and specificity has identical value or weight, Jordan index indicate the maximum threshold on a ROC curve as a maximum value of a difference between true positive rate and false positive rate. At the same time, the maximum Jordan score can be achieved when model doesn't make mistake while predicting negative class, so basically when false positive is 0. In this case, true positive is equal to the number of positive instances in a database, and Jordan is calculated as a ratio between number of positive instances in database and number of positive predicted by the model. As both equation 1 and 2 express the maximum value of iodine, then they both equally identify the optimal point on the ROC curve. So in our proposed approach, we took expression number 2 and formulate the rewrite formulas of Matthew coefficient and F measure using this parameter maximize iodine. On this slide, you can see that formula number 4 and formula number 6 is received for Matthew correlation and for F measure using the maximized iodine expression. And we can see that the Matthew coefficient is basically a function of two parameters, is a maximized iodine and the ratio between negative instances and database and the negative instances predicted by the model. And F measure is a function of maximized iodine. Having formally defined Matthew coefficient and F measure where maximized iodine gave us possibility to obtain objective difference in the metrics and use them in the approach in the algorithm to support a decision making. The algorithm that we created consists of 3 blocks. The first block define and calculate measures. Each include the calculation evaluation of a binary classification model by different methods. In our case experiment, we use Matthew correlation coefficient and F measure, and calculate P difference between those methods and maximize iodine and save those difference. In block number 2, we calculated the significance of the difference using predefined maximum difference, accepted difference, which we denoted as a threshold. When the difference is less than a threshold, it is marked as a not significant. In the last block, all differences which are marked by a flag not significant are ranged, and the matrix with the smallest difference value is proposed by the algorithm. In case when algorithm didn't find any matrix with a flag non-significant, it suggests that fuzzy analysis is needed. In the conclusion, we specify the following. In the current research, we define Matthew coefficient and F measure as a function of maximized iodine, which give us possibility to calculate the objective difference between those metrics. The obtained definition gave us possibility to calculate unbiased difference in the matrix P squared, and this difference is not received as in previous study when the ROC curve cutoff is equal to 0.5, which not obviously optimal and may never be selected by scientists for the model's prediction. The defined calculation are used in the proposed algorithm to support the scientists to select a method in order to evaluate the binary classification model for predicting the technical conditions of the construction object. And the novelty of the proposed approach is that it recommends a metric considered optimal cutoff of the ROC curve, and this improves the accuracy of the model evaluation. Thank you for your attention. Appreciate your questions.